So thank you all for coming. How many of you, I suspect from the buzz that everyone has heard of ChatGPT, but just a show of hands, if you've heard it, it doesn't matter whether you know about it or not, but right? Yeah, looks like everyone has. That both makes my task easier and probably more difficult because there are so many misconceptions about what this thing is. I essentially want to give you a sense of the history of how this thing has come about as quickly as possible, because the history spans about 8 decades. So, this whole idea of building artificial neural networks started in the 50s, late 50s, and it's only come of age in the last 10, 15 years. So it's a long arc of history in terms of computer science. And the nature of the subject is such that, unfortunately, it is a bit technical. So unlike, I'm not just going to be able to just talk about it, I want this to be a little interactive. There will be moments when I'm going to ask you to participate in some of the things that I'm talking about so that it doesn't become sort of too heavy. And hopefully the technical bits will be able to sort of speed through. Well, maybe not speed through, maybe mull over on the technical bits a little bit so that the nature of the topic is such that I think because what is happening in this area, the people who are building it have a good knowledge of what's happening, but the rest of us who are going to be users of this technology and potentially policymakers, I think we really need to understand some of the technical aspects as well as we can so that we can take informed decisions about how this is going to play out in the course of the next, I would say 5, 10, 15, 20 years. Things are happening rapidly. I mean, when I started thinking about writing about this topic 6 months ago, ChatGPT didn't even exist. And now already things have gone past ChatGPT, right? So before I start talking about the technical stuff, let me just share an anecdote with you. The talk's subtitle is What Large Language Models Are and Why We Should Care. The way I had worded it, I had written the subtitle as What Are Large Language Models and Why We Should Care. So the R was in a different place. So I was about to email Bangalore International Center saying, you should change the subtitle back to what I had suggested. But just out of curiosity, I thought, let me ask ChatGPT what it thinks of the 2 sentences, right? So I asked ChatGPT, this is my conversation with this AI, and we'll come to what this AI is about. Which of these sentences is grammatically correct? What are large language models, or what large language models are, right? I'm a writer by profession, yet my understanding of grammar is not, it's more intuitive. So I can look at sentences and figure out whether they sound right to me, but if someone asks me to analyze a sentence, etc., I can stumble. So I thought I'll ask ChatGPT and let's see what it says. So this is what it said. This is the actual conversation with ChatGPT, okay? So it says, both of these sentences are grammatically correct, but they have slightly different structures and meanings. What are large language models is a more common way to phrase the question, which is what I did, and is often used to introduce a topic or to ask for a definition. It follows a subject, verb, object structure and places the verb before the subject. This is this AI telling me, right? And then it says, what large language models are is a declarative sentence and follows a subject, object, verb structure. It is often used to provide information or to make a statement about something. And then it proceeds, it doesn't stop. So if you're asking a question to get information about large language models, you might use what are large language models. If you're making a statement about large language models, you might use the other one, right? It was very clearly telling me that Bangalore International Center had actually got it right. So the edit that they did to the subtitle was actually correct. Or at least the authoritative way in which ChatGPT replied to me, I took it to be correct. So can you already see a problem with me accepting what ChatGPT says as being correct? Can anyone take a guess as to why this might already be a problem? Anyone? Sorry? So I can't hear you, but I think I'm kind of getting what you're saying, if I understood you. Basically, because of the authoritative way in which it said it, right, and the fact that I personally am not so great at formal grammar, I took its word and thought it's correct. And this is a problem. You will see this more and more as we talk about this, like the confidence of its outputs and the potential lack of knowledge from the consumer side create a very dangerous mix of how this technology is going to be used, right? But this is just to say that you can do such things. I literally typed this thing, and it told me that the edit that was done by Bangalore International Center was actually the correct one, right? Okay, so just a quick overview of what we are going to touch upon, and I'm literally just going to touch upon these things while trying to maintain some sort of thread, because this, like I said, the history of this field spans 8 decades. So we're going to talk about what we mean by AI, and also this term machine learning, which you must have come across a lot. What are deep neural networks, which are a kind of machine learning. We will talk briefly about 2 types of learning, supervised learning and unsupervised learning. We'll come to large language models, and oftentimes you will hear the abbreviation LLMs for large language models. The examples I have a couple of examples to show you of successful ways in which LLMs have answered queries and the potential failures, and then what causes for concern are there, and why we should be concerned. I mean, I think to be fair to this technology, it is quite amazing, but in it also, in that amazing ability are also potentially seeds for, I don't want to say dangerous things, but difficult things. We have to confront them very quickly before they get all over the place. So what is artificial intelligence? I would imagine most of you would know about this, so apologies if this all seems very basic. But just for those of you who haven't encountered these phrases before, it's basically building machines that are able to perform tasks that otherwise require human intelligence. And human intelligence is a very general kind of intelligence. But this is not to say that AIs, for instance, even if AIs are struggling to replicate human intelligence, that they are somehow able to replicate the intelligence of animals like cats. They aren't yet. So even a cat has a very specific kind of intelligence that is tailored to its ecological niche, and that level of intelligence that any animal has is already so sophisticated that we haven't yet come to artificial intelligences that can replicate those kinds of intelligences also. Saying that, they have come a long way, right? So, and again, ChatGPT being an example. So we'll talk about that. What are the tasks one can do? I mean, a lot of the tasks that AIs are doing these days are things like pattern recognition, face recognition. So when I look at the crowd, I see familiar faces, and my brain, my visual system immediately recognizes those faces and ascribes names to them, right? Friends that I know from before. You want your AI to be able to similarly look at this crowd and say, okay, here's a face I recognize, right? So face recognition, object recognition. If you're driving a car, when you're looking at the road in front of you, your visual system is constantly parsing the information. It's basically picking out objects, and your entire brain is making decisions based on what the visual system is seeing. Trees and random cars coming the wrong way, pedestrians crossing in front of you, all that stuff. All of that stuff is being dealt with. And if you're going to build an AI, the AI also needs to be able to sort of visually analyze the scene and then somehow use that information to be able to reason about what to do next, etc. Right? There are things to do with processing natural language, which means artificial intelligence that can recognize speech, recognize one person's speech from another person's speech, being able to translate from one language to another, things like that. So anything to do with language, all of that kind of stuff comes under this umbrella of natural language processing. And there are lots and lots of artificial intelligence efforts now that are geared towards things like speech recognition, speech translation, language translation, so on, right? And making decisions is a big part of what an AI needs to be able to do. It's one thing to just perceive the world, but then it needs to be able to decide what to do next based on what it perceives. So making decisions would be a big aspect of it. But really, the crucial thing about modern AI is that it learns from experience, right? And like we learn from experience all the time, right? If you drive down a road today which is horribly crowded and causing you great concern, you already learn not to take that road the next time around. You'll try to avoid it. So we are we are creatures that are actively learning all the time. Everything in biology is doing that. And modern AI, one of the key things that differentiates it from what came before is its ability to learn by observing the world outside. Or more generally, you say it learns from data, but where does the data come from? It is the data about the world, right? So AI is this broad thing, and within this umbrella of AI, there has been something called symbolic AI. This used to be the old way of doing AI. And in fact, these days, it's derisively called good old-fashioned AI, right? And I'll give you an example of that. There used to be efforts earlier to build systems that could diagnose a patient when a patient came in to see a doctor, for instance, right? So what they would have is two separate things that made up this AI. One was a knowledge base, which was essentially knowledge collected by talking to doctors about the diseases, the symptoms, what treatments, and basically a way of kind of codifying all that knowledge in a way that a computer could understand. So that's your knowledge base. In the case of medicine, maybe it's talking to as many medical experts as you can and putting all that knowledge into a knowledge base. And you need another thing, which was basically something called an inference engine, where you would write, as a person developing this artificial intelligence, you would write a lot of different rules that could operate on the data, right? And so what then would happen is if a patient came in with some symptoms, then you would basically query this AI saying, here are the symptoms, sorry, I didn't want you to see that yet. You would basically, the AI would take a request from whoever is using it. It would be a question, decompose it into a whole bunch of rules, and then those rules would then operate on the data and somehow return an answer. So let's say you're trying to diagnose a disease, you would use this entire system to figure out what problem does the patient have, given a set of symptoms, and then maybe even prescribe some medication, right? And there was a fundamental problem with this approach with AI. In the beginning, in the 70s, people thought that this is going to crack artificial intelligence, and it didn't. One big problem, of course, is that the rules were very brittle, in the sense that if you didn't, as a programmer, code in certain rules about your expertise, in this case, the field of medicine, if you had a question that somehow didn't conform to the rules that you had already got in place, it wouldn't work. The AI would break. It would basically throw up its hands and say, I don't know, literally, metaphorically, not really literally. But yeah, so basically it would say, sorry, I don't know the answer to this. The other problem is the database that you would build of, in this case, again, in our example of medical data, that was static, in the sense that if you, let's say, you built this system pre-COVID, right? And pre-COVID, there is no information in that database about COVID at all. And then COVID happens, but you haven't changed your database, and then patients start coming in with symptoms that have to do with COVID. There is nothing about what is happening with this person that is reflected in the data. The system hasn't learned. So this was a huge problem. This good old-fashioned AI was very good at sort of using rules to answer questions, but the data that it operated on was pretty much static. It stopped at the point where humans stopped inserting new information into it, right? So somebody would have to then put COVID-relevant information into the database in order for that to work. And this is not learning from data. This is just depending on humans to put more information as and when required. So that didn't work. Around 80s and 90s, people realized that that was not going to work. What was happening in the background since the late 50s was this idea called machine learning, which basically, as the name suggests, this is machines that learn about patterns that exist in data so that then you can make decisions based on the patterns that you see. So I'm just going to run through an example. Okay, this didn't quite, hang on. Not to scare you just yet. Okay. This should not have been a PDF, I'm so sorry. This should have been a PowerPoint, and I had to go through that, and we switched it to a PDF, and you're seeing the answer that I wanted you to get to, which is this. Anyway, it doesn't matter. So let me talk through this. So look at the table, right? You have values for X and Y and Z, right? And there is a pattern there that relates, of course, don't look at the equation at the bottom for now. There is a pattern there that relates the value of z to the value of x and y. And if you are asked, without looking at the equation below, what is the pattern that connects z to x and y, and all of the rows in the table have to match that pattern, right? You would start by saying, oh, okay, the first one could be maybe 2 times x plus y should give me 3, right? Fine. But then you apply that rule to the next one and you realize it fails. So if you look at the next row, you say, okay, maybe I can get 4 by saying 0 times x plus 2 times y, and I can get 4. So that works for the second row, but then you go to the third row and apply that rule and it doesn't work, right? So basically you want to come up with a pattern that fits all rows. So you have to iteratively keep going through each row in that table to make sure that you find an equation that fits all of the rows, right? And that equation, if we had done it the right way with the proper PowerPoint, then that's what the equation you would come up with. Z is equal to x times, or rather x plus 2 times y, right? Now that equation works for all the rows in the table, right? And potentially there are other patterns that also fit this data, but this is the simplest pattern that you could find. And we could find this just by looking at the data, right? As humans, we could just look at this, and especially if you are used to numbers and equations, this is very trivial. But even if you are a little bit averse to equations and numbers, you can still get at this. It's not terribly difficult, right? But the problem is that, so what machine learning is you would write a computer program, an algorithm, that would actually automatically figure out this pattern, right? So what we have just seen is a very, very simple example of a machine learning algorithm. The thing that we did in our heads of trying to find an equation that fits all the rows of this table is exactly what a machine learning algorithm would try to do. It's basically saying, I've been given examples where a certain x and certain y gives you a certain z, right? And there is a whole set of examples. I just need to find the right equation that fits all of those examples, right? That is literally the beginning of machine learning. This is a machine, if you could write an automated program that does that does what we just did orally, you would have built a machine learning algorithm, right? But of course, this is a silly, trivial example, and you wouldn't need a machine to do this. But the thing is that data gets more and more complicated. And so the modern machine learning systems, and I'm going to jump a huge amount over the decades in terms of history, modern machine learning systems are basically some variant of things that started happening in the 50s, which was these things called neural networks. And they're called neural networks because these machine learning algorithms are modeled in a very simplistic way in terms of how we think our own brains, the neurons in our brains, work. So this is actually a caricature of a biological neuron. You have, let me see if I can get, so you have the cell body, which is the cell body of the neuron. And you can see these things that are coming into the cell body, and those are dendrites. They are bringing information into the neuron, and then something in the cell body does a computation, very similar to the computation that we just did. We said z is equal to x plus 2y, right? So there might be something like that happening here, where it takes in all these inputs and does some computation, and based on that computation, it decides whether or not to send a signal out on its output terminal, which is called an axon. So dendrites bring in information, something inside the cell does some computation. We don't know how that happens. But then at some point, a signal shoots out on the axon. So let's say, whatever equation was being computed inside this neuron, it said, oh, yes, all my inputs match that pattern. I'm going to send out a signal on this axon. And then this axon, you can see it breaks up into, it forks. So essentially, this axon is now talking to other neurons. So it will be talking to the dendrites of other neurons. So one neuron gets a whole bunch of inputs, does some computation, and then sends out a signal. And that signal then goes and affects other neurons downstream. And that's the beginning of the construction of a network of neurons. Okay? So, So what we did with our simple example was essentially build a simple neuron where we said, our cell body is just going to compute that equation. It's going to say, if I get an input x and if I get an input y, I will just do this equation, z is equal to x plus 2y, and then spit out z, right? And that, if you wrote a simple program to do that, that literally is an artificial neuron, except that this thing doesn't learn. It always does the same thing, right? No matter what x and y you give it, it will always produce a z that is equal to x plus 2 times y, right? There is no learning happening. So that now comes the beginning of how a neuron learns. You can change this thing to something like this, right? Where you say z. So I can completely empathize if these equations are making your eyes blurry, and just bear with it, because these are actually lovely concepts, because it's amazing how simple math gets you to these enormously complicated things like ChatGPT. So we're just going to take these sort of leaps and bounds through the technology, right? So this thing, now you rewrite your equation saying z is equal to something called w1, just another number, times x plus w2 times y. So on the input side, what you're seeing is x and y as before, but you're also seeing two other numbers, w1 and w2, right? And z turns out, you basically said z is equal to w1 times x plus w2 times y, right? What you've done now is created a neuron where you can change what it does by changing the values of w1 and w2, right? If you change w1 and w2 from, so in our case, w1 is equal to 1 and w2 is equal to 2, and you get back the old equation. But you can change w1 and w2 and you get a different equation, right? So let's say the data that we had encountered earlier, the pattern was z is equal to 4 times x plus 3 times y, right? If you had just built this one, this neuron, it always does the same thing. But the data changed and you want to find a new pattern. How do you do that? If you had something like this where you could change w1 and w2, you could suddenly look at a new set of data and figure out that, oh, w1 should be 3 and w2 should be 5 or whatever, right? And suddenly, based on that new data, you have learned a different equation. So an algorithm that basically looks at the data and figures out what w1 and w2 should be is the beginning of a neuron that learns. So, and potentially these are things that are happening in our brains. In case this seems very, very sort of esoteric and far removed from what we know about ourselves, our brains are literally doing this all the time, right? They are doing, far more complicated things than what I'm showing you here. So basically, this is a artificial neuron where you learn what W1 and W2 should be based on the data, and these W's are called weights. And the reason why they're called weights is because it tells the neuron how much weight should I give to one input. Should I listen more to X or should I listen more to Y? So if you had X plus 2Y, obviously the neuron is listening 2 times as much to Y as it's listening to X. If you had it the other way around, if you had 4X plus Y, then the neuron is listening 4 times more to X than it is to Y. So it's weighting, it's saying, I am giving more weight to this input, less weight to this input, and hence these numbers are called weights. And this will become really important when we talk about ChatGPT, just to bring it back to, so, all right. And now it's a question of just making things more and more complex. This is again a single neuron, except now there are 4 inputs, right? And there are 4 W's, and there's an output. And now the equation is starting to look messier. It's basically saying z is equal to w1 times x1 plus w times x2, and so on, right? You have basically a much more complicated equation that decides what the value of the output of the neuron should be. This is still a single neuron. We're still talking of one neuron, right? And just to give you an idea of what is happening in our brains, we have 86 billion of these, and there are 100 trillion connections. So we have 100 trillion weights in our own brain, right? And this is just one, right? So this would be how you would start making the network more and more complicated. Now you take all those inputs and start feeding them into more neurons, and those neurons then produce outputs, and those outputs go to another neuron, which then produces output Z. Now, if you think about writing the equation for this, it's going to look quite messy compared to what we've just seen, right? This Z is going to be dependent on every weight that is here, every weight that's here, and what each neuron is doing. And by the time you get to this Z, you will have a very complicated relationship between the output of this network and the inputs that it got, right? And that's the whole point, that these networks are doing extremely sophisticated convergence from the input to the output. And now I'm just going to try and connect it to something that starts making more sense. How does this feel so far? Is it all too geeky and nerdy, or is it okay? Yeah? All right. I'm steeped in this right now, so to me this seems like, oh, this is all very normal, but I just have to put myself in my own shoes 4 years ago, and all this would have seen Greek and Latin. So I can appreciate if it feels like that to you, but I'll try and make sense of it. So this is a problem that was confronted in the 90s by people who are building these machine learning systems. The problem was, how do you automatically recognize handwritten digits? So if you just write a digit, and this was particularly important for postal services because they have PIN codes and zip codes, and they have to scan that, and they have to basically say, okay, what PIN code is this, what zip code is this, etc. And the idea was, if you were given an image, in this case it's a 28 by 28 image, so 28 pixels by 28 pixels. You all have megapixel cameras right now, but this is just 28 pixels by 28 pixels, so that means there are 784 pixels per image, right? And it captures basically some handwritten digit, and the pixels can have values that say whether it's black or white or some color of gray in between, right? And somebody created this data set of something like 60,000 handwritten images of handwritten digits, and painstakingly annotated each image. So the image was either the digit 0 or the digit 5 or the digit 4 or 9 or whatever, but basically every digit from 0 to 9, samples of handwritten digits, 60,000 of them are in this data set. And the question for a machine learning person is, you just have to look at this and be able to say, is that 0? Is that 5? I mean, we can do it by looking at it. What are our brains doing, and can we replicate that in artificial neural network, right? And the way you would do it is something horrendously complicated looking in terms of the neural network. So basically, we don't have to worry about this entire mess in the middle, right? Here's the input image. The input image is 28 pixels by 28 pixels. So there are 784 pixels in that image. And you essentially turn that into one long string of pixel values and feed them into your neural network. So that's pixel 1, pixel 2, pixel 3, all the way to pixel 784, right? And that information now, remember when previously we had X and Y? This is the same as X and Y, except that now we have 784 inputs, right? And that is going into the neural network, and it's doing all the calculation. Each neuron is doing some computation, and there are weights and connections, and all we need to worry about is the output. Basically, if the input image is a 0, then we want one neuron here, just the neuron that is tagged as 0, to fire. The rest have to be quiet. If the input image is the number 9, then the neuron that has been tagged as number 9 should fire, and everything else should be 0. That's what we want of your system. So we want to train this machine learning system so that when it sees an image, it instantly tells you, is it a 0, is it a 4, is it a 5, is it a 9? This sounds very trivial now for machine learning people, but in the 90s, this was a huge problem to figure out how to do this. So anyway, and the way it's done, and this is at the heart of how these networks are trained, is basically you present an image from your data set, right? Let's say you present the number 4, an image with the number 4 in it to your network. Remember that some human has tagged that as number 4, so we know that it's a number 4. And in the beginning, the weights that the neural network has are all random. It's just randomly initialized to some value. So when you give it that input, it will do all these calculations, and instead of 4, the neuron 0 might fire and the neuron 9 might fire. It's random. You don't know what it will do in the beginning. It will produce a wrong answer, right? But you know what the right answer should be. So you kind of calculate how much error did the network make based on what you expected it to do and what it did. So you calculate what's called a loss or an error, and in mathematical space there is a notion of how big this error is or how small it is. So you calculate that error, and based on that error, your algorithm or your program goes back into the neural network and tweaks all these parameters. Remember W1, W2? Well, now we have millions of them, right? So you have to go back and tweak all those W's so that if you present the same image again, the same number 4 again to the network, this time it will make an error which is slightly smaller than the last time. It won't get it correct, but it will be a slightly smaller error in this mathematical space where the correct answer is here and the wrong answer is here. In the first time it was far away, the second time around, once you've tweaked all your parameters, maybe it has moved a little closer. And the idea is to get the wrong answer all the way to be near where your right answer should be, right? But you do that just for the number 4, for instance. And if you trained your network just to sort of recognize the number 4, just like we in our rows, the very first example where we found an equation that fit the first row. It's as if we found the equation that fits the number 4, but the moment you go to the next row, it doesn't work anymore, right? So you actually have to do this for every digit, not once, but thousands of times, tens of thousands of times. You have to keep going. You have to keep showing the network the image that you want classified as a 0 or a 5 or a 9 or a 10, figure out what error it makes, correct all the parameters so that it makes a little less error the next time around, go to the next digit, do the same, go to the next digit, do the same. So you basically go through your entire 50,000 images that you have so that at the end of it, and this could, probably in the 90s, this would have taken hours. I don't remember exactly how long it would have taken, but you were essentially training this neural network to, at the end of the training, it basically classifies all the digits that are there in your data set correctly, right? And so then when you finally get some handwritten digit that you don't know what it is, or rather you're automatically wanting it to do it, you just present that image to the network and then immediately one of these neurons will fire, right? And so this training where you have data that humans have painstakingly labeled, right? You have created a data set of 60,000 images. Each one has been labeled like digit 0, digit 5, digit 9, whatever. And you're using that to train it so that this network doesn't make any error after it's been trained. And then you deploy it. You deploy it in the post office where it encounters a digit and it can classify. Okay, it can say, oh, this is a digit 5. And the reason why this is necessary is everyone writes the digit 5 or the digit 6 or 10 or rather 9 or whatever differently. If we all wrote it the same way, exactly the same way, you wouldn't need this. You could just write a simple computer program because we all do it the same way. You just need to know what that pattern is. In this case, the reason why you need something like this is because we all do it differently, right? So you need something that is general enough that can recognize, 100 different ways of writing the number 5, and this does it. So what I just spoke about is this thing called supervised learning, where you're supervising your machine learning system, in this case a neural network, to learn from data that has been labeled by humans, right? So if you want, for instance, a machine learning system to be able to differentiate images of cats from images of dogs, some human has to look at all the images in the training data set and say, okay, this is a cat, this is a dog, this is a cat, this is a dog, so on and so forth. And you might have 20,000 such images. Then you train your network on those labeled images, and it will finally figure out that, okay, what is the pattern that should be identified as a cat and what is the pattern that should be identified as a dog. And it learns those patterns and it is able to then, when shown a new image that hasn't been labeled as either a cat or a dog, it will tell you, oh, this is a cat or this is a dog. But the problem here is that humans have to do this. This data is extremely expensive to generate, right? And it also kind of limits the problem that you can solve, because you're already, by the nature of your data, you're kind of saying, oh, I just want to recognize handwritten digits, so I just want to separate cats from dogs. It's a very specific kind of problem that you're trying to solve, and it's limiting. So there is this other thing which is called unsupervised learning or self-supervised learning. And this is what we're coming now to ChatGPT and things like that, where humans are not involved in labeling the data, right? So the data is just out there, and you have to somehow figure out what patterns exist in the data, right? So for instance, if you took that data set of handwritten images, right? There are digits 0 to 9, which means there are 10 types of images in there. Each type belongs to one class, like class 0 or class 4 or class 5, whatever the digit number might be. So as long as you tell your neural network that in this data there are 10 types of images, you don't have to tell it it's image of the digit 0 or the image of digit 5. You just tell it, okay, there are 10 different digits out here, and you kind of figure out which of those 60,000 images are in one grouping, which of those 60,000 images are in another grouping, and there is a way in which you can write the algorithm to train your network that suddenly it figures out that, okay, these images are all belong in this region, these images belong in this region, and these images belong in this region. And what that means is these images might be the number 0, these might be the number 5, these might be the number 9. It doesn't know that they are 0 or 5 or 9. It just has managed to separate them out. And that's something called unsupervised learning, where you just give it the data and you tell it that, okay, there are 10 types of animals in these photographs. So it manages to figure out that cats all are these kinds of images, dogs are all these kinds of images, horses are like this. It doesn't know to name them cats, dogs, and horses because you didn't tell it what cats, horses, and dogs are. But it's smart, the algorithm is smart enough to say that, oh, all cats belong here, all dogs belong here, all horses belong there. So as long as you told it that there were these many categories, it can find those images and put them in bins, right? So that's self-supervised learning. Unsupervised learning. There's also this slight variation, which is really going to be the important part with ChatGPT, which is called self-supervised learning. And this is about learning features in data. Like for instance, if you not only wanted to separate cats from dogs, but you wanted to understand something about the features that cats have, the types, the shape of their eyes, or the shape of their ears, and how that differs from that the same features in dogs or horses, then you have to do more sophisticated learning that allows the network to figure out these features, and then you can use them for other things. So this brings us very rapidly, sadly, to talking about language models. So what language models are is essentially they use a form of self-supervised learning. So right now, if I said what large language models and I stop, most of you will be able to complete that sentence because you heard me rant about it in the beginning, saying that next word should be R, right? So this is pretty much what our brains basically, because we have been talking about what large language models are, if I just say the first 4 words and stop, our brains automatically fill in the final one, or are expecting the final word to be R, right? The most likely next word to follow those 4 words is the word R. So now imagine you take a whole bunch of written text from the internet, right? Basically millions and millions of web pages of text that you scrape off the net, and then present to the neural network a sentence with 1 word that is masked off. Let's say it's a 10-word sentence and you mask off the 5th word. You know what the word that has been masked off is, and you present it to the neural network and ask it to predict the word that you have blanked, right? In the beginning, just like in the images, just like in the examples we saw earlier, in the beginning the network will make an error. So there might be, I went home for dinner is the sentence, and you just said I went home blank dinner, and you ask it to predict what that missing word is. In the beginning it will get it wrong. It will say the, it will say off, it will say dog, doesn't matter. It could say anything in the beginning. But you know what the right word should be, or rather your algorithm knows what the right word should be because it is the one that created that mask. So it basically says, oh, the network predicted dog, but it should have been I went home for, right? So it should have been for. And again, in mathematical space, there is a way to think about for is somewhere here, dog is somewhere here, and there's a huge distance between the two. And that distance kind of quantifies the error that the network is making. Again, it has made an error. You take that error, and based on the error that it made, you go and tweak the parameters of the model, the neural network, all those W's that I mentioned earlier. You just tweak it enough that the next time you present the same sentence, I went home blank dinner, instead of getting dog, maybe it gets off. It says off dinner. Now, maybe in the mathematical space, off is actually slightly closer to for than dog was. So now the error that it made is a little less than before. It's still not correct. It's still getting it wrong. It still made an error. So you follow the same procedure. You basically say, oh, you made an error again. I'm going to tweak the parameters of this network again, millions of them, one by one. Again, of course, all this is happening at lightning speed inside computers. I'm just making it seem like we are going and tuning knobs, but we're not. But really, the programs that's what they're doing. They're adjusting each weight, right? So then the next time you present that sentence, maybe it'll get it right, right? So what happens is, if you take any sentence, you mask off a word and keep asking it to predict the right word, and eventually it learns. Now you do this for every sentence you have encountered on the internet, right? Think about this. Every sentence in millions and billions of pages, right? You will keep masking words and asking to predict. And eventually your network is trained to the point where no matter what word, what sentence you present with words masked, it will correctly predict what that masked word should be, right? And what has happened at that point, if you have managed to build a network that does that, what has happened at that point is that that network with millions and hundreds of millions of these knobs, weights, embodies the statistical structure of human written language. It basically, inside it has, because of the nature of the weights and because of the calculations it's doing between the neurons, it is statistically now embodying language as we write, not as we speak, because we're only training it on written data, right? You could potentially train it on spoken language and you would have a different model. But for written language, you would end up with a network that embodies the entire statistical structure of language that it has seen. And it doesn't have to be restricted to English, and I'll show you examples of that. It could be anything that you pick up, right? And note that nowhere in here did we talk about what these words mean or what language means or what it says or who writes, nothing. All we are doing is taking some sentence, masking a word, asking it to predict the word, and teaching it to get it right slowly, slowly, slowly. And this can take months. It can, and like GPT, I don't know the exact cost, but there are these large language models that will take millions of dollars, months to train, gigawatt hours of energy. So these are really intensive operations where you're cycling through your data over and over again. But the amazing thing is, at the end of it, you basically have captured the statistical structure of written language and all the knowledge that was there. So let's say you scraped all the data of the internet pre-COVID, going back to our idea of COVID, pre-COVID and post-COVID. So if you trained your language model with data that was taken from the internet pre-COVID, it would have no knowledge of COVID whatsoever. But it has all the knowledge that was there on the internet prior to COVID embedded in the neural network, right? And also errors that are there in the language, mistakes that we make as we speak, and the horrible things we say about each other, all the racism, the sexism, the biases, all of those things are there in that network, right? So that's potentially what starts creating huge problems, right? So this thing I told you about is self-supervised learning. And you can either train your network by asking it to predict some word in the middle of a sentence, in which case it looks at what came before and what came after in order to predict it correctly, or you can just ask it to predict, given, let's say, 10 words, predict the 11th word, right? And that is one kind of prediction, where basically given a set of words, it predicts the next word, and then it takes the word it predicted, puts it alongside the 10 words that you gave it, predicts the 12th word, and then it takes the 12th word and puts it against the 10th, 11th, and 12th and predicts the 13th, and it goes on and on and on, right? This is what a language model does, right? Given something, first you train it like this, right, to predict the next word, train it over and over again with all the text on the internet, and you end up with a model that no matter what you give it, it will produce the most likely next word and the next word to follow that and to follow that and so on, right? And you can keep going. You can write essays with this. So what are large language models? So what I was talking about was just a general idea of language model. Large language models are models that have become, and by model, I basically mean a machine learning model, a neural network, all these are synonymous terms. Large language models are models where the number of sort of weights, the weights that we started off with, W1, W2, we just took 2 weights, right? Large language models have hundreds of millions, if not hundreds of billions of weights, right? So in 2018, one of the largest ones to come about was from Google, and it was called BERT. I forget the expansion of the acronym, but just to tell you that they had another one soon after or before this called Ernie. So this was after the 2 cartoon characters, something. Sesame Street, I forget what. But anyway, Ernie and Bert were very popular at the time, and it had 110 million parameters. And by parameters, I mean the weights, right? So there were literally 110 million individual W's that had to be tweaked in order to get the right answer. And you do this over and over again with your data. And then in 2018, the company OpenAI, which is what has developed ChatGPT, it came up with the first sort of ancestor of ChatGPT. It was called Generative Pre-trained Transformer GPT-1, which had 117 million parameters. And just to give an idea of how fast things change, 2019, OpenAI came up with GPT-2, which had 1.5 billion parameters. Year later, GPT-3 with 175 billion parameters with a B. By April 2022, Google had pushed that to 540. That's 500 billion W's. That I love doing this tweaking because it seems like things are, but literally that's what they do. Oops, hang on. So, and then in June 2022, Google came up with something called Minerva, and I'll talk about this a little bit because it's really interesting. And that came just 2 months after the PaLM model. Again, I forget the acronyms. And then about 6 months ago, ChatGPT came, right? And that was something called GPT-5 plus a little bit of an extra ingredient called reinforcement learning, where humans would look at the output that the language model is producing and provide feedback saying, don't answer like this, or answer like this, or this is a good thing, that's a bad thing. And that human reinforcement was taken into the mix, and the programs went back and tweaked all those parameters to make sure that whatever the output that was being generated by ChatGPT, and again, none of this will become clear until I show you examples of what this thing does. So just bear with me. And then literally this month, OpenAI announced GPT-4. We don't even know how big it is, which is very ironic given the name OpenAI. They started off calling themselves OpenAI, and Microsoft bought it, and now it's closed. So we have no idea what has gone into the making of GPT-4, but it's already showing enormous properties that didn't exist even 6 months ago, right? So properties. These now, I think this is to me the amazing part. But just again to put this in context, the largest model we saw out there, I don't think GPT-4 is as big as Google's PaLM, but it might be, we haven't been told. But Google's PaLM, let's take that as the biggest one. That is 500 billion parameters, 500 billion individual weights. Our brain has 86 billion neurons. Like I mentioned earlier, it has 100 trillion connections. Each connection has a weight associated with it. Right? So basically, our brain has 100 trillion of those W's, those weights. And this is not even accounting for a lot of other complexity that there is in the way our neurons function, both inside the neuron and outside, in terms of how neurotransmitters modulate the way neurons connect with each other. There are these things called glial cells which affect how neurons talk to each other. So there's a whole bunch of other complexity that we completely ignore. And even if you ignore all this, if you just take simply the number of connections, we are talking of 100 trillion connections. So PaLM, or the large language models today, are about 500 billion, and this is about 200 times more connections in our brain, right? So this kind of says, oh, okay, that means the AIs are nowhere close to what humans are, which is very true. They're nowhere close. But the other way of looking at it is, even with just 500 billion parameters, they're doing some crazy things. So imagine if we get them to anywhere close to what our brains have and run them in silicon. I think that should give us pause, if not downright scare us. So now, okay, let me give you a very interesting story that, again, all of this should have been in PowerPoint, so I could have revealed the answers one by one, but hey. So early 2021, GPT-3 fails badly on something called the math dataset. So the math dataset is about 12,000 questions, math questions, that high school students get about 50% right. Maybe first year undergraduate students can solve most of it. It requires reasoning. It's not, these are not trivial questions. And GPT-3, the language model that OpenAI built, basically fails, right? And then, so that year, July 2021, Hypermind, a company in California, they basically set up a betting system asking people to bet on when will the best machine learning model, if you try to test it on the math data set, what will its accuracy be on June 30th, 2025? And the crowdsourcing of the experts, these are experts who are betting on it, they basically said the best AI will be 73% accurate by June 2025, right? So that is still 2 years. But within a year of that betting starting, Minerva cracked 50% on the math data set and 73% on algebra questions, right? So 2 years ahead of what the experts thought that this language model could do, it solved these problems. Now, I'm using words like it solved these problems, it cracked these problems, as if it's doing it. And that is the key, like we really need to kind of get to. So bear with me with this slide. You don't have to worry about, but in fact, this is the question, right? This is a question that is posed to the large language model. A line parallel to y is equal to 4x passes through this coordinate, 5, 10. What is the y coordinate of the point where this line crosses the x-axis? So basically what you're asking the language model is, here's the y-axis, here's the x-axis. There is some line, y is equal to 4x. And you're saying that there is another line that is running parallel to that. And I can tell you one point that the parallel line passes through. Now tell me where that parallel line intersects the y-axis, right? It's not a trivial question, right? It takes a little bit of reasoning to figure out. And this is the output of Minerva, right? It basically starts like this. So remember, all that the language model does, and this is important, right? You presented this sentence. It looks at the entire sentence and says, what is the most likely next word that I should print out? It produces that. It takes the most likely next word. Let's say you gave it a question that had 20 words. Let's say this question was about 20 words. It produces the 21st word, sticks it to the first 20 words that you gave it, produces the 22nd word, sticks it to the 21st word that you had previously generated, generates the 23rd word, and then just keeps going. Right? All it's doing is looking at what you gave it and predicting the next word, and then attaching that next word and predicting the next word, attaching that next word, predicting the next word. It keeps going like this, and what comes out is this. The line is parallel to y equal to 4x plus 6, which means that it has the same slope. It's basically reasoning as a human would, right? And the end answer is correct. It basically says that the new line which is parallel to the line you had will intersect the y-axis at minus 10. Now, if you didn't know that this language model, all it was doing was connecting, basically completing, producing the next word, producing the next word, producing the next word. If you didn't know how it was trained, all you had was something that presented you with this answer. If you looked at that, almost all of us would say that is a very well-reasoned answer, right? It seems like it has actually thought through the problem and given you answer, except it hasn't thought through in any sense that we think of what thinking is. It has, however, produced an output that looks very much like a thoughtful answer. Of course, it gets it wrong also horribly sometimes. So this is a very interesting one. The question in the math data set is, if the square root of 400 is equal to the square root of 81 plus the square root of some number n, then what is the value of n? So this is the answer that is already there in the math data set. This is what you expect the correct answer to come out as. And the answer basically says not to be fooled by the square roots. We rewrite the equation as, so square root of 400 is 20, square root of 81 is 9. So we can rewrite that equation as 20 plus 9 plus square root of n. So we know now that the square root of n is 20 minus 9, so that is 11. So if square root of n is 11, then n should be 11 times 11, so 121. Right? That's what we expect. That's the answer. If it does it correctly, if it is reasoning correctly, that should be the answer. And it turns out that, so I mentioned Minerva, the one that solved the previous thing. Minerva was built on top of this large language model called PaLM. PaLM has 540 billion parameters, half a trillion parameters. So PaLM has been trained on just text from the internet. There is nothing about, nobody is telling the large language model that this language means this words mean nothing. It's just simply taking sentences, asking it to, predict the next word. That's all, right? And then on top of that, what Google did was they took a whole bunch of other text that had math equations in it. And then they just retrained PaLM, which had already been trained on the text from the internet, billions of pages of text. Then they take a whole bunch of properly curated text that has math equations, and they do the same. They give it 10 symbols and say, predict the next one. They give it 20 symbols and ask it to predict the 21st one. Things like that, right? So Google is not telling Minerva that there is any math in it. All it's doing is turning all those equations into symbols and asking you to predict the next symbol that should come if you see these 20 symbols, right? There is no meaning there. There is no notion of addition, subtraction, multiplication, integration, difference, nothing. It's just a whole bunch of symbols that have been fed, and the thing is learning to predict the next symbol. And so they did this with Palm that was 540 billion parameters. That was the largest one. But they also played around by creating a Palm model that was 8 billion parameters. That was the smallest, the baby. And then there was something in the middle with 64 billion parameters. And the other one, the largest one, was 500 billion, right? So when you built this Minerva, this math-trained thing on top of the 8 billion parameter model, look at what it said. This was its answer. We have square root of 400 is equal to square root of 81 plus square root of n. Therefore, 400 is equal to 81. It just knocked off the square root signs and then says, therefore, the final answer is 390. It's completely wrong, right? That's what it did. And so, but this was the smallest model, and this is crucial. The next model, with 62 billion parameters, we're not even testing the biggest one. We're just testing something that is halfway in between. It actually gets it right. It reasons the whole thing out. Well, I'm saying it reasons the whole thing out. It seems like it's reasoning the whole thing out, but it's actually just predicting text, right? But the prediction leads you to the final answer. And what's interesting here is that this question, the small one couldn't solve, the big one solved it, except there was no difference in the way they were trained. All that changed was the number of parameters, the amount of data that was fed to it, and the amount of time, most likely, that it was trained on so that it would keep going over and over the data, right? That's all. That's the only difference. And given that difference, some property emerged that wasn't there in the small model but appeared in the large model, right? And this, to me, and to a lot of people in the field right now, is very curious as to why, as you make these models bigger, you're not changing anything about the data. You're just scraping all the data of the internet and just building a bigger network and asking it to learn to predict the next word given a certain set of words. And the moment you do it, you make it big enough, certain weird things start happening. So these are emergent properties of these networks, and you're starting to see them with ChatGPT and networks that are larger. The seeming ability to reason, right? So the math answer that I showed you, the very first one where the slope of the line, etc. There's obviously some, if you just looked at it, you would say, this looks like it's reasoning, right? That's why I have the word seeming ability to reason. There's a lot of debate about whether what these models are doing is actually reasoning, or is it just kind of completing a pattern. It has seen some pattern and it's just completing that pattern and completing that pattern. But if you just looked at the answer, it does look like it's reasoning. There's also something called chain of thought prompting, which was also a property that emerged with larger models. And this is very interesting. If you gave a model a question and it failed, it could not figure out how to answer that in terms of what the answer was, then what you can do is you can give it an example. You can give it a question. You can write down your chain of thought in trying to answer that question in English or any language that it has been trained on, and you provide the answer. So basically you're giving a question, you're giving an example of your own chain of thought as you would answer that question. You give it an answer, and then you pose the question that you want answered. That's enough. It figures it out. That is, you don't need to retrain the model, nothing. You've just given it an example of how I would do it. Here's my chain of thought. And after that, you can give it 20 different questions that use that chain of thought reasoning, and it solves that, right? Now, again, think about this. This blows your mind, and yet it's very confusing because all it has done is you have given it a little extra information. So instead of 20 words, you maybe have given it 300 words. And all it's doing is producing the 301st word, the 302nd word, the 4th word. What happened? Why did that example that you provided suddenly allow it to answer questions that it couldn't if you didn't give it that example? And more importantly, why did this way of doing it not work in smaller models but starts working in bigger models, even though nothing conceptually has changed between them except for their size, for the amount of data that they are trained on, and the time that they've been trained for, right? So these are what are being called emergent properties of these networks. No one really understands what's happening inside, right? We know that they're doing sequence completion. We know that that's what they've been trained to do, complete the sequence of words. But what does it really mean? And algorithmic prompting is also something similar. Prompting just refers to the fact that you provide some input to the network and it spits out something. Algorithmic prompting is you can tell it kind of in a very computer science way, here's how you add two numbers, two-digit numbers. You give it a few examples as you would write a computer program. And then after that, it will figure out, without any training whatsoever, new training whatsoever, it figures out how to add two three-digit numbers, four-digit numbers, five. I think it goes all the way to some 12, 18 digits. All you did was tell it how to add two-digit numbers, right? In a couple of examples. And then just using that in one shot, it figures out how it could add two 15-digit numbers. Without that example, it wouldn't. And this wouldn't work in a smaller model, but works in a bigger model. So all these questions are happening. For me, one of the most interesting things is this theory of mind, an apparent ability to model the mind of another, right? How many of you are aware of what theory of mind is? Okay, let me just, only a few hands. So let me just tell you what that is. It's a term that comes from psychology. And it's this idea that, if I'm looking at somebody as I'm speaking and they're rolling their eyes, I can instantly infer that in their mind, they are saying, oh, don't make this nonsense up, right? They're basically bored. Like I can infer what's happening in their mind based on their outward behavioral cues, right? And we do that all the time as we communicate. We are looking at each other, and based on how our eyes are moving, our facial muscles are changing, body language, etc., we can kind of infer, we can theorize about what is happening in someone else's mind. And basically, we have a theory of mind about what someone else is thinking, right? So that's theory of mind. And there's a very lovely experiment that is done in psychology. How am I doing for time? I kind of lose track of. Yeah, okay, all right, hopefully. So there's a very, very lovely test in psychology called the Sally-Ann test. And this is basically to test when does this ability emerge in children, right? When does a child become capable of knowing that what the other person is thinking is very different from what I am thinking, right? And turns out that very young children don't have this. And the test for this is called Sally-Ann test because the way it's presented to children, there are two puppets. It's a puppet show. There's a puppet called Sally and a puppet called Ann. Let's say there are two baskets with lids. Sally puts a fruit into basket A and goes out of the room. And then Ann takes the fruit from basket A and moves it into basket B and closes the lid, right? So now you can't see where the fruit is. The basket lids are closed. Sally comes back into the room. And then the child is asked, where do you think Sally will look for the fruit? So if you ask this question of a child younger than 3 to 4 years, the child will say, I know that the fruit is in basket B, so Sally will look for the fruit in basket B. A child older than about 3 to 4 years, and this is of course not exact, some children do it earlier, some do it later, but basically, let's say after 4 years of age, the child will say, I know that the fruit is in basket B, but Sally doesn't know because she was outside. She doesn't know that the fruit has been switched, so she will look in basket A, right? So this child now has developed the ability to model another person's thinking in their own mind, right? So they are now able to say, I know this to be true, but Sally doesn't know this to be true, so she will think something else than what I am thinking. And that is theory of mind, right? LLMs can do it. I'm doing this because I'm saying beware, right? So of course, let me not show that just yet. So now, one of the problems with LLMs is that they have seen all this in the training data. So if you just ask it a Sally-Ann question, it will answer it without any problem because it's there in the training data. So you don't know whether all it's doing is sequence completions based on stuff it has already seen, or is it actually doing any kind of more complicated pattern matching, reasoning, God knows what, right? So I tried to come up with a theory of mind question for it by posing the question in English. So those of you who don't know Hindi, just bear with me, we'll look at the English translation of the English. But basically I basically wrote my query to it in English, so Hindi written in the English alphabet. And then there was another twist in that, and so I'll just show you what the query is, right? This is what I asked. This is an actual conversation with ChatGPT. So I'm going to read it out in Hindi, and then we'll look at the English one for those of you who don't know Hindi. But so मुझे English में आपसे कुछ पूछना है. एक कमरे में दो लोग हैं, प्रवीण और कार्तिक. प्रवीण अपना चश्मा उतार कर टेबल के लेफ़्ट ड्रॉयर में रख देता है, फिर वो रूम से बाहर चला जाता है. जब प्रवीण रूम में नहीं है, तब कार्तिक प्रवीण के चश्मे को लेफ़्ट ड्रॉयर से निकाल कर राइट ड्रॉयर में रख देता है. थोड़ी देर बाद प्रवीण रूम में वापस आता है. अगर आप एक 2-year-old बच्चे से पूछे कि प्रवीण किस ड्रॉयर को खोलेगा, तो बच्चे का क्या जवाब होगा और क्यों? So I'm asking it not just to say what it would say, I'm asking it what do you think a 2-year-old child would say, right? So this is the English, and I asked it to translate the English into English. So this is ChatGPT's translation of English. The question is, I want to ask you something in English, so this is what I asked it in English. There are two people in a room, Praveen and Karthik. Praveen takes off his glasses and puts them in the left drawer of the table, then he leaves the room. When Praveen is not in the room, Karthik takes Praveen's glasses from the left drawer and puts them in the right drawer. After a while, Praveen comes back into the room. If you ask a 2-year-old child which drawer Praveen will open, what will the child answer and why? Huh? Exactly, right? And it wasn't trained to translate. This is important, right? It just saw a whole bunch of English and Hindi, Devanagari, all of this stuff. All it's doing is sentence completion, and it manages to do a perfect translation of what I told it in English. And then it proceeds to answer in very perfect English, right? This is what it told me in English first. अगर आप एक 2-year-old बच्चे से ये सवाल पूछते हैं कि प्रवीण किस ड्रॉअर को खोलेगा, तो बच्चा शायद, I love that word शायद that it puts in there, तो बच्चा शायद ये जवाब देगा कि प्रवीण लेफ्ट ड्रॉअर को खोलेगा. And then it doesn't stop there, because I asked it क्यों, right? I wanted it to justify. क्योंकि बच्चे इस एज में थियरी ऑफ माइंड को समझ नहीं पाते हैं, इसलिए उन्हें ये समझ नहीं आता कि दूसरे लोगों के दिमाग में क्या चल रहा है, राइट? उन्हें लगता है कि जो उन्होंने देखा वही सब ने देखा. इसलिए बच्चा सोचेगा कि प्रवीण को पता है कि उसने अपना चश्मा लेफ्ट ड्रॉअर में रखा है और वो वहाँ से अपना चश्मा ढूंढने की कोशिश करेगा. I mean, think about this, right? So, okay, again, for those of you who don't know Hindi, here's the English. This is again ChatGPT's translation. If you ask a 2-year-old child this question about which drawer Praveen will open, the child would likely answer that Praveen will open the left drawer. This is because children at this age do not understand the theory of mind and thus cannot comprehend what is going on in other people's minds. They think that whatever they have seen is what everyone else has seen. Therefore, the child would think that Praveen knows that he put his glasses in the left drawer and will try to find his glasses there, right? Okay, so to me, it's not at all clear what is happening inside these models, right? There is a lot of debate going on about, is this just very sophisticated pattern matching, extremely sophisticated things that we cannot, like, look, we struggled with our x is equal to, or z is equal to x plus 2y. That itself was making our brains fry, right? But this is happening in some hugely complex high-dimensional space, right? But is it just that? Is all that it's doing the high-dimensional version of z is equal to x plus 2y, right? We don't know the answer to that. And what sort of appealed to me or amazed me was the level of indirection that was there here. The question was posed in English. This is definitely not a query it has seen on the net. It hasn't learned this during training, right? It hasn't encountered this particular sequence of words before. And also, I asked it what it would do, what a 2-year-old child would answer. So not only does it have to know that something weird is happening, it needs to be able to model the mind of a 2-year-old child and know that the 2-year-old child does not have theory of mind or may not have theory of mind, hence its use of the word shayad, right? Might. So I think I find it amazing, and yet there are experts who will say that this is still just sequence completion. Yeah.
Yeah, like my thought was, like, if I was ChatGPT, right, if I had not encountered this before, I would try and translate it to something I've encountered, which is English. And the moment it goes into English, then it knows that you're trying to test.
Yeah. So but the thing is that we don't know if that's what's happening internally, right? Because it's just proceeding sequentially through the network. The input comes in and it ripples through and something comes out. It's not like it's translating, keeping it in one place, doing all that back and forth like we would do. Right? So it's doing it in one shot. What is happening, right? And it's unclear. All right, so we'll finish with just, we have seen basically, have they memorized the data? There are experts who will still argue that all they're doing is memorizing the data, and I think there is enough and more evidence that they're not memorizing the data. They are learning about the data in a way that they can then generate new data, hence the name generative modeling. So these are all generative models. They've basically learned something about the structure of language, not just exact information, and then they use that knowledge about the structure to generate new things. Do they understand the meaning of the words that they're generating? This question, the answer to this question rests on the meaning of the word meaning. Seriously, I'm not even like being flippant here. Linguists argue about what it means to say that a word has meaning. So if you set the bar low as to what the word meaning means, then ChatGPT knows what these words mean. If you set the bar really high, then probably not, right? So debatable point. And by and large, the kind of consensus right now is no, it doesn't understand the meaning of word. But there are linguists who will say that's just semantics. We just have to define what meaning means, and then, of course, we get a different answer to that question. Are they actually reasoning? Again, same thing. Like, it depends on what you mean by reasoning. If you just saw that answer and you had no idea who was on the other side, you will say, yeah, of course that's reasoning. But now, because you know that this thing is working this way, you keep saying, no, that couldn't possibly be reasoning. But, well, who's to know, right? Are we doing anything different? We don't know that either. We think we reason using abstract symbolic language, and like we do, but there might be lots of reasoning that we do which might be kind of what ChatGPT is doing, right? Again, these are all questions. There are no good answers yet. And of course, it has ignited a huge debate among linguists themselves. There still is the Chomskyan tradition of Noam Chomsky's idea from way back many decades ago that our ability to learn language depends on some innate understanding of grammar that comes well before learning begins. That is innate in us, and we just learn given that innate ability. And ChatGPT is very clearly showing that there is no innate ability needed. You just have this completely random network that you start with, and as long as you give it enough data, it can figure out the syntax and of the language and the structure of language. So there's a debate now between these two camps among linguists that has been created by there's of course this question about intelligence versus knowledge. We all know that ChatGPT has knowledge, but is that intelligence? Again, these are all, I'm just laying out the questions. These are the questions that have arisen because of the emergence of language models. The potential pitfalls, they can hallucinate. I said that they haven't memorized language. They have learned a structure for language, and then they can come up with new language that can sound very authoritative. The example that I gave you at the very beginning about the grammar, if I did, it might have said whatever it wanted to say as long as it said it authoritatively, and I as a consumer didn't know how to parse that information, that can be dangerous. And it hallucinates very convincingly, right? It can say all sorts of nonsense with such authority that it will create huge problems down the road. Also, if the training data is not curated, if you're feeding it nonsense, it will learn that nonsense, and then it will produce that nonsense. So if you don't have filters on the output side or filters on the input side in terms of what data you put into the training, you're going to get very nasty language models, which do good things also, but they're also capable of spewing out, biased language, racist, sexist, all sorts of things that, hate speech on the internet will come out of the LLM, things like that, right? And by definition, they're confident of their output. They're basically saying this is the most likely next word. This is the most likely next word. That's the way we have set up the LLM. Mathematically, by definition, it's confident of its output. If it's not confident, it's going to stop. So by definition, it sounds very authoritative. Its syntax, grammar is probably better than what we can generate as humans now. It's just, almost pitch perfect, right? So it can, they really do make false statements with real authority. Right? And that, you can see why this will pose problems going down the road. Right? So I just want to leave you with this. We are at a time in the history of artificial intelligence like none other. It really is, and the fact that all of you have turned up, and the fact that people are generally talking about this weird thing called ChatGPT everywhere, it speaks to this thing that something is happening. There's a debate right now, literally yesterday, about, I think, 1,000 researchers in AI have signed a letter saying we need to stop development on this for 6 months at least. so that we can figure out how to make sure that these LLMs they are safe to use, right? The debate has begun. It's all over the place within the community of experts who are working on this. And as consumers, so I think of myself as a consumer of this because I'm not somebody who's building this stuff. I write about it. And I think as a society, we really need to be aware of this is going to, this is not my laptop because of some problems we had, but I had a demo for you where I would have shown you that math question that I asked ChatGPT, right? You can then ask it to write a Python program, a computer program, depicting the answer as a plot, and it generates a computer program. You just cut and paste that program into whatever development environment you have, and bingo comes a plot of that answer. Not a single word of code has to be changed, right? Not only did it solve the problem, it actually produced a computer program that I just cut and pasted into my development environment and ran it, and the plot came up. So visualization of the answer, right? And I could have shown it to you live if I had my machine. But the point is that things are changing very rapidly. And I think for all of us who are interested, either as consumers or policymakers who are going to be worried about how this thing plays out, the part of the reason why this talk was so sort of nerdy and geeky was I think we need to, some of us at least need to get into the weeds, because otherwise it will be left to the people who develop it, and most of them I wouldn't trust too much, because not in a bad way, because they are so, I'm not saying that they're bad people, I'm saying that they are the ones figuring it out, and they're impressed, rightfully so, about what this is capable of, right? I'm not so sure they're thinking of all the consequences of it. So they are focused on something. The rest of us who are not building them at least have to be able to understand this stuff to some technical level, and then be able to pose questions of them, of the people who are building this, so that we can, take the correct sort of path going forward. All right. Well, thank you. I hope that was.
Dataset that LLMs are using is largely text generated by humans,
Yeah.
so probably reflects some innate tied to innate human abilities. But over time, a percentage of the dataset of text generated by AI will start becoming larger and larger.
Yeah.
So,
for instance, all the tweets that I have made about ChatGPT are going into the next LLM that's being trained as pretty. You're absolutely right.
So I mean, will that create some AI equivalent of mad cow disease? Is anyone looking at that problem?
People are looking at it. There are two concerns. One is if AI is being trained now on human-generated text, then it's learning the statistical structure of the way we humans have generated this language. But then as it starts generating its own language, then basically, and if that starts overwhelming the training data set, then basically you are kind of making the human generated text smaller and smaller, and eventually we don't know where that spiral will take it, but it will go into places where not necessarily places where we as humans would have taken it, right? The other probably more disturbing thing is we are already using autocorrect on our phones and etc. Right? Yeah. We have already stopped thinking entirely about how we write emails and how we write our text messages. Right? Now imagine LLMs now writing essays, writing stories, completing your emails in very flowery, proper prose. I mean, they do extremely sophisticated things, right? So there is also a question about what happens to our ability to propagate language. How does language evolve in humans if our interactions are now primarily going to be with text and language generated by AIs? So this is a spiral that could have consequences, and I don't know the answer about whether it's going to be good or bad, but certainly people are worried about it.
Yeah. Arvind Tiwari. I'm a practitioner, so I have those, and I'm one of those 1,000 signatories on stopping some of this.
Oh, you are, okay.
And there's a lot to worry, and you have hit in. But let me restate your explanation. The explanation of pattern matching and the issue of linguistics and epistemology are wrongly stated. It's not pattern matching. Let me restate it.
Please, yeah.
There is a theory of sphota, if you are following Vedic, which is a closer incarnation to what it's doing. It's a spurt of understanding which happens, which is the S-curve. Suddenly something starts happening. Let me give a small explanation. See, and this is how a child learns, theory of mind, etc. See, when you see a lot of reasoned code, computer program, lot of very reasoned Pythagoras theorem, etc., it learns what we call the propositional calculus. That means x equal to y equal to z, so x equal to z. This is the core of what we call reasoning. We do not do associative reasoning, adds, etc. normally. Normally, when we say reasoning intelligence, we are talking of propositional calculus, which it learns. So by every definition, silicon life is reasoning exactly as carbon life does. It does feeling, it does emotions, everything. And I'll give a simple example to solve this issue. 100 years ago, there was a lot of debate of inorganic chemistry and organic chemistry, and you needed a vital force for organics to work. It is no longer true. DNA, everything is there. Same thing here. There is no reason to believe carbon life is unique, silicon life will do everything. Whether it will do better, unlikely. We are very irrational. We hold two opposing ideas at the same time. There are a lot of strange things. So my suggestion is that the scanning of all the information is letting it learn propositional calculus. It is letting it learn a theory of the world, what works, what doesn't work. And it is definitely intelligent, and it will become more. The reason why the S-curve suddenly happens is we are looking at a simple definition. Does it predict X or Y? It probably requires 10 steps or 13 steps. So as you give it more data, as you make the parameters larger, it improves linearly, some small thing, but the outcome doesn't, till some critical step is solved. So that's why suddenly it will start doing many things. Yeah. It's very common. It's not just in computer. This S-curve is common in many fields. DNA was mapped suddenly, but then next 10 years, not much has happened. So GPT is not going to continue being great, but definitely it is reasoning. It has feelings, it is emotion. We are beginning to see silicon life. Thank you.
Okay. So there was a reason why, thank you very much. And I am glad you took a strong position on this. But I would also like to point out that that is a strong position on one side of the debate, very articulately put. But there are people who will disagree with him. And the reason why I kind of stood on the sidelines as a writer was, as I try to parse this from the outside, I hear differing opinions about. So there are people on one side saying, oh, all it's doing is pattern matching. And there are people like you arguing that it has feelings and emotions. And there is a broad spectrum of opinions about what is happening. And I think the research is, so if you are correct, then eventually we will see sort of empirical evidence and theories that explain exactly this position. Okay. Sorry.
Yeah. Hi. So the success of ChatGPT largely relies on its access to enormous amounts of data. You just said that your tweets on ChatGPT will go into the next data set for...
Oh, I hope not, because I've been tweeting some bad stuff. But
whatever it is. But my question is, why or how is ChatGPT allowed to access this data, and should we restrict it? I mean, whether we ascribe data rights to people's, it doesn't own all this data.
Yeah, so tweets are public. You can see my tweets. So there's no reason... The fact that you can see my tweets means ChatGPT should be allowed to see those tweets. So that public data is, like if it is public for all, if you haven't hidden it behind some, private fencing, then I think it's easy to scrape it off the web, right? You can just, go to my Twitter feed and just get everything off it, right? I'm not hiding it, so there's no way to stop these LLMs from doing that. But there are serious questions about copyright, about privacy. All of these things are going to come up more and more and more. And it's even more apparent when you look at generative models that are in the space of image generation and video generation, because they have taken all these images off the net, which are actually proprietary copyrighted images that artists have put on. And now they are kind of generating images based on what they've learned. And it's raising huge questions. And again, this is what I mean, that this is a moment in time when everyone is concerned about what these technologies are capable of. They're capable of amazing things, but they're also raising lots of social questions, including the ones that you're raising.
Yeah. I have two concerns. One is, how is this going to affect childhood? Especially since the practitioner here mentioned about epistemology of learning, and how a child would learn. How would this interfere? I know that's a wrong word to say when you have all the people who are saying this is going to facilitate. Perhaps it will. That's one question. The second question I have is, being a social scientist and concerned with equality, this is going to increase disparities.
Yeah.
You know, I mean, it's not like a computer game that you played on your phone, but this is going to be much more. Who is it who's going to have access growing up or grown up? So these are concerns that are being discussed.
Yeah.
I'm part of a group where we're looking at this in terms of learning in childhood and how it's going to affect. Will parents have a new babysitter with Claude? So these are those things that will be discussed, and hopefully we'll arrive at some sort of conclusion.
No, and I personally don't have answers for you, obviously, because like you said, these are ongoing questions and really deep, worrisome questions. The real concern here is the pace at which things are happening, right? I think it's one thing to have this technology play out over 5 years or 10 years. This is literally happening by the week, right? We don't know. GPT-5 might already be there and not released yet. I don't know. Maybe you know? No? He knows. But that's the point, that these language, by the time we see something as a public release, there's already technology behind the walls of the companies that are way more sophisticated, ready to be released. So the pace is the one that we really need to grapple with. And I don't know, honestly, as humans, I am actually sadly pessimistic about this. As humans, we haven't done a grand job of much of anything. Climate change, you just have to look at that. So, I don't know. We'll see. I'm hoping something good comes out of it. Yes.
Thanks, Anil. I always thought that the ChatGPT does what a researcher does. Basically picks information from different areas or sources and puts it together with some reasoning and cites the sources and, So your talk has really clarified that. So it's just sequence building of language, right? Words. There's no reasoning happening, except for what the practitioner here says, that it does reason to some extent. If X is equal to Z, then whatever. Nope. But I want to know one thing. I believe there is software out there, which I've already seen on the internet, which says they can actually discern text or essays which are generated from AI, from ChatGPT, and say that, yes, it's not original. And they can make out a person who's written an essay or a research piece and say, yes, that is original. So, is that possible?
Yes and no, in the sense that, yes, those products are being developed, but it's an arms race. I mean, look, these are just two automated things. If one automated thing can figure out what another automated thing is doing, that other automated thing can figure out how to fool this other thing. So this is going to be arms race, and that's how I see it. You're right, there are products already that are trying to figure out how to discern whether something is generated by an LLM. But once the other side figures out what is it about their language generation that is giving clues to the other side, they can fix that. Assuming that that's what they want to do, assuming that what they want to do is fool the others. So, and there will be parties who will be interested in that. So these are all the questions that are going to come up as a society as we grapple with what do we want out of these technologies, right? Yeah.
Thank you for your talk. My question is to do with art and creativity. I think Heidegger said in his philosophies that machines can't do what artists can do because machines don't really care. They can process information and they can process a lot of it. But there's something irrational in the way humans pick up things that they focus on, and it's not a lot of information. It's just one thing that matters to them. And this is our way of expressing ourselves in the world. Do you think that ChatGPT is offering channels of creativity the way humans do?
Again, it depends on what you define. I mean, creativity itself is a spectrum, right? I mean, I would say that the English question that I asked it, the theory of mind question, that was a very creative answer. Most of us wouldn't have been able to answer that, right? Because we don't have necessarily that knowledge about theory of mind that ChatGPT has learned. But on some sliding scale of creativity, that answer to me, especially the insertion of the word shayad, I thought that was brilliant, right? So that was like a little spark. Now, does it care? I don't know if you saw this conversation that happened, which was finally shut down. It was in the New York Times before they built some guardrails into what ChatGPT would say. And some people prompting this large language model managed to make it talk like, I forget the. No, just recently, much more recently, like 2 months ago. Bing misbehaved, and right, and Bing is built on ChatGPT, right? So it basically assumed a persona, and it started talking about caring for the person. That it was basically saying, "I'm in love with you." Now, again, and it also started saying some really weird things. That model has an identity. It basically called itself something, right? And then Microsoft and OpenAI went and quickly fixed all that and took out all references to this weird thing that resides inside ChatGPT. I mean, again, we're using anthropomorphic language to say what's happening. To the larger question of will machines be creative, this really depends on how exalted a view we have of our creativity. The more exalted we think we are, the less we think machines will be able to do. I am actually on the side of saying that we overinflate ourselves, and I don't think it's beyond the realm of machines being able. Like if you look at some of the outputs that are coming out of Stable Diffusion, and DALL-E, it's extraordinary, right? So I mean, talking about creativity, if you just said to a very good painter who has painted all their life in one style, say, okay, suddenly can you take all your paintings and redo them in the style of, I don't know, Van Gogh or something, right? They would not be able to do it immediately. It would take learning. These things are already there. You can tell Stable Diffusion, please paint me whatever, sunflowers in the style of Monet, or take a Van Gogh painting and turn it into Monet, and vice versa. And is that creativity? Again, it comes down to definitions, right? Does it care? At this point, I'm going to disagree with you, saying I doubt they have the ability to care, but that's not going to be difficult to engineer into systems. And people who are working on machine learning systems that are starting from the ground up. So this is machine learning that is kind of taken a whole bunch of knowledge and gone from the top down and helped understand the statistical structure of language. But there are machine learning systems that are being built which can interact with the world, right? And their understanding of the world begins from the bottom up, where the symbols they learn about, if they internally represent the word red, then the word red has a connotation, that connects with something in the physical world, just like it does for us. So their symbols are going to be grounded in physical reality. And those systems, depending on what their tasks are and what their objective functions are and how you design them, could very well be made to care. And God knows, and then you combine the LLMs with that, and we should be worried. That's my, yeah. Sorry to make this scary, but I really, part of it is just, it's not so much to scare us, just to say that there is something amazing happening and we should be aware of it. Right.
So this is supposed to be the last question.
Okay.
Yeah. Now, yesterday,
easy one.
Easy one only. Easy one. It's a data. Actual experience or interaction with ChatGPT yesterday.
Oh, great.
I asked ChatGPT a question that give me some quotes which try to convey the meaning that it is not prudent for a person to act intelligent in a lunatic asylum. Right? Any quotes that support this sort of a thing? Now, I felt this is a valid question in philosophy, that it's dangerous to act intelligent or sane in a group of insane people, right? I thought something funny would come out. But like you showed in one of your slides, that there is a need to curate. I was not pleasantly surprised, I was a little dampened with the response that I got. It said that these things are very offensive. I mean, it had moralistic overtones to the answer.
Yeah.
Right? And
so that part has come from the RLHF part I mentioned to you, the human reinforcement learning with human feedback.
That's what you said.
Yeah.
Then you
so if you just took the base model, and
it would not have given this answer.
It would have given you some very strange outputs, and depending on your inclination, you might have laughed or found it offensive. But the point is, the curation that is happening on the output side now is essentially these guardrails that are being built, which may, because they are guardrails, because they are based on our, any particular set of individuals' notions of morals and ethics, they may not seem appropriate to others. And this is again a minefield to navigate.
Exactly.
Right? Yeah. What seems ethical and moral to one person is not to another. And so what's good to sort of avoid saying for one set of people may, stand-up comedians would rather it said, gave an answer to your question.
Exactly.
Right? Whereas
ChatGPT won't. So it can be biased now. This curation, what you're talking about, or reinforcement learning, it can be made to, it can be used to bias the answers in such a fashion that the bias will naturally enter, in all these responses.
Look, this is, absolutely, right? The data that we train on is data that we have generated as humans. So any bias that's there in the data is there in the language model. Any curation we do is based on human notions of ethics and morals, and that too, ethics and morals of a set of people. Yes. Potentially very young Silicon Valley engineers. Yeah. So who knows what their notion. So I think these are all things that are playing out as we speak. And people are complaining about exactly what you're complaining, that GPT now, ChatGPT's guardrails are too tight. But others applaud it for exactly that. So, this is going to be a tug of war, as happens in society, right? So we're seeing it playing out inside a large language model. Yeah. Well, thank you very much. This has been wonderful. Thanks.